Welcome back. Good morning. Um, Hopefully everyone's doing well. This is our last day of sort of new material before the exam. So we've got Thursday will be a review day. So just to kind of get you situated, um, we're doing today related rates 12.5, which should help you as you look back to 11.6, implicit differentiation, because that's what we're going to use. We're going to use that tool of implicit derivatives in today's lesson. So those two will get connected. My last class was a little, as I said, it just seems like there's so much stuff that we're doing, but a lot of the sections relate back to one of the others. So it's almost like there's half the stuff if you think once you get things organized. So just to kind of after today, again, you should be able to go through 12.15, 12.6 elasticity. What's going on here? Maybe it's that. I think I'm on the. There we go. Is extra credit. So if you don't do it, you got 0 out of 0. It's not going to hurt you. If you do it, you will get it. You don't have to do it now. It will be available for you all the way till the end of the class, so even during finals week. So you can get those and kind of see, maybe you say, I don't really need it. But it's not too bad. There's a lecture in there. So where were we? As you start to prepare for the final exam, for the exam 2, in fact, after this, I go and get a root canal, so that it'll help, but I'm not looking forward to it. So actually, let's just hang out here all day. I hate root canals. I've had too many of them. So I added this, I think, on Monday morning. I found some other videos. I think I have it later in the course, but what this is it's a review for all of the sections, section by section. So what I did is I went into the PowerPoints and I kind of took the main things, and so I do maybe a 5 or 10 minute summary, and then I work through the questions from the exam review, for one of the exam reviews. These are a little bit older, so they keep updating the exam reviews, but a lot of the questions, they don't change. What I will do is there's another exam review, and I'll compare, and by Thursday I will highlight any differences. But again, the content's all the same. So these have me working through some of these questions for each of the sections we've done. So you can kind of go back and forth, and once you kind of narrow down, like 11.6 and 12.5 today that we're doing are connected, maybe what we do today will help you go back if you still had some questions from 11.6 or vice versa. Anyway, it's a good way to review. So you've got the solutions. The other thing that's here is you'll kind of like you see here as I work through here, I also included the PDF of the session itself. So you've got just what was written. So you might not want to take the time to watch a 30-minute video. Some of them are 20 minutes. Internet's a little slow, but there's PDF files that have everything just kind of written out. You might just look at it, oh, I see what's going on. But in the video, you'll see me writing and explaining as I go. These are the end results. So they're just all the solutions. And again, they've got the answers down here to the questions. So I kind of we'll see let me know how this works. I'm not quite sure what I did to test 3, but this one I did for test 2. So there's that. And I highly recommend going through section by section, looking at those. There's a WebAssign review. I think there was 40 questions. We don't have one of those anymore. They stopped doing it maybe a year and a half ago. But some of those homework questions may be similar to some of the ones that you're doing because they are out of WebAssign. So you might take a look and fast forward, and you might find something that's helpful in there. So that's why I've left that. because the test is paper pencil, they favored the review. And then this one is just a link to the most current paper or PDF file with the review and the answer key. And that's what we'll highlight on Thursday, kind of going through that, and I'll make links back to other things that are available. And then, of course, if you need me, Friday is always a good day to arrange for a Zoom call. Just contact me. We can set something up. And even over the weekend, because we'll have our test on Tuesday, I'm open to meeting up for 30, 45, 50 minutes, whatever it takes, answer a few questions. There's also, ASU has tutoring here on campus. There's also some online tutoring, so all those resources. But let's go ahead and get into our, actually I've got it here, our final section for the test. And this is what's called related rates. So there's two variables that are changing, but they relate to each other. Thus the term related rates. The thing that we're going to have to do here is we're going to be using that implicit derivative. Remember where we took the derivative of y and x, and we had a marker for dy dx. Well, this time we're actually going to have three variables, and one variable is invisible, time. So things are changing over time. So we won't actually, in any of these, see a variable for t itself, but we will see one quantity changing over time and another quantity changing over time. So in a business setting, how many DVD players our company makes, that changes over time, and that affects the cost. That's related to the cost. The more we produce, supply demand type thing. So there's those kind of things going on. We've got a circle, the radius is changing. Of course, if you change the radius of a circle, you change the area of the circle. We've got some balloons being blown up. So the amount of volume inside changing will change the radius as well. So those are the related rates. So part of this is like in, what was it? I think it was 12.2 was a very heavy duty problem solving. And that's kind of what we get here. Not quite as bad. Most of the things are going to be set up for us. So we'll give you the concept. That's basically the rundown. Is we're going to identify two variables that are related to each other and changing, and then there's this third variable, time. So as a little bit of introduction, let me get my pencil, my pens. There we go. Go back to slideshow. So, this is basically saying what I did. We'll have some quantity changing. They call it Q, right? And then as it changes over time, its derivative would be the derivative of Q with respect to time. So dQ dt. In our examples that we're going to work through, area is one of the things. So we've got a circle. The area of the circle is changing. Its rate of change is its derivative, right? So this is where we make the connect that the derivative is the rate of change. It's the instantaneous rate of change. And so the derivative is dA dt. And then oftentimes with a circle, we have a radius, right? Or of a sphere or something. And when it's changing, that's going to be dr dt. Okay? And we're going to see in all these questions that we're going to be solving, we basically need to get it set up, get some equation like area of a circle is what? Pi r squared. So that one we have to remember. When we get to the volume one, they will give it to us because it's a little bit more complicated. But pi r squared, we're going to get that set up. The problem will give us some information, but we need to take its derivative because we want to know how things are changing, not how things are static. Remember, algebra and geometry, area equals pi r squared. Calculus, the derivative of the area, how is the area changing as the radius changes? That's a derivative. Okay, so that's the first step. And then we'll plug in all the numbers we got, and it'll just kind of solve itself. Um, so again, nothing overly new, but just getting it set up. So first we need to identify what are the changing quantities, and then we need to use mathematical notations, which means find the equation. And again, this is more general step-by-step stuff that doesn't make sense until we actually start doing it. So we're going to do it, but I'll give this sort of overview. We may need to draw a diagram. If we've got a circle, let's draw a circle, put a radius, we'll label some things. We've got to find our equations. Area equals pi r squared. And then we will take its derivative. And again, this is implicit derivatives. We're going to have two derivatives, the derivative of area, the derivative of radius, and both of those are with respect to time. So there's this dt, but we don't see any t variable. It's kind of in the background. Things are happening over time, but we don't have it directly in there. In the question, they may say that the time period is like every week. This is a weekly production schedule or a yearly. So that's kind of there, but it's not directly in the question. And once we've got the solution, oftentimes that allows us to get a solution. Sometimes we need to go back to the original, plug it in. We just need to know what they're asking. Sometimes they're asking what is the rate of change of this other thing that we didn't know. So we'll just look for what the question's asking. So let's just so from here on out, we're just going to work several different examples. I pulled some directly from the homework. And we'll just see how this is. And again, it's just going to be sort of reading through, getting what our variables are, finding an equation that fits it, and then taking a derivative, and everything will come together. Okay, so we'll start off here with the radius of a circle is increasing, and we can see we've got a rate. So what is this 10 centimeters per second? Well, that's how the radius is changing over time, right? So we've got centimeters and we've got seconds. This must be dr dt. Okay, so remember, whenever you see the word rate, that is a derivative. And in this case, it's a constant. So it could have been a function. It could have been 10r or something, or 10t or something. You know, it could be changing over, but it's a constant rate of change. So they're kind of being nice to us because they could make it a little bit more complicated. They could have the time in there, but it's a constant rate of change. Then the question. So here's our question word. How fast is, and again, it's got two things. It's got the question, but it also tells us they're asking about a derivative, right? Fast is a rate. It's time. How fast is the area increasing? So we know our other variable here at the instant when the radius has reached 5 centimeters. Okay, so this 5 centimeters, that's not a rate, is it? It is an amount. It is a time when r equals 5. Okay, so now how do we set this up? Well, we've got area, we've got radius of a circle. We got area of a circle, radius of a circle. How are they related? Mathematically, the area of a circle is equal to pi r squared. And that's one that they don't typically give it, so we've got to kind of remember that. It's easy to get this confused with the circumference. Remember, circumference is 2 pi r, but this is area. So Google it, or however you want, make sure you're working with the right formula. And then before we start plugging any numbers in, though, this is area and radius. We don't have any rates of change in here, right? How do we get rates of change? We take the derivative. So we're going to take the derivative of area, derivative of, and think of a now as a variable. If you take the derivative of a to the first power, what do you get? You get 1. Derivative of, think of x, derivative of x is just 1, right? But then we put our marker that we took the derivative of area with respect to time. Okay, and that's that invisible part. We know things are changing over time, but it's not directly in there as a variable. Okay, remember this is implicit derivatives. Over here, pi is just a number. It's not a variable. It's 3.14 blah, 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 right? It goes on forever. So we just listed as pi, but it is a number, okay? It's a constant multiplier, so it goes along. But then I look at r. R is a variable, r squared. How do I take the derivative of r squared? Well, that's going to be the 2 comes down, and I'll put it in front of the pi just to make it look how they usually do. So the 2 came down, and then we subtract 1 from the exponent, so that gives us r to the first power. And what did we do? We just took the derivative of r, so that is dr, with respect to time. So notice there's this sort of this unspoken thing that's happening here, that things are changing over time. So it just, I don't know, even when I'm doing it, it still feels a little weird. Why can we just do this? Well, because these things are changing over time. Okay. Usually in algebra, we're just, we're given a radius and we want to calculate the area. It's static. It's not changing. Calculus, things are changing. And if things change, there's this quantity of time, this dimension of time. Okay. So that's the main thing. I'm going to erase this 1 now, just because it's kind of a helper. 1 times anything is there. So now do we know? Let's look back at the question. dA dt, how fast is the area increasing? That's really our question. So notice we've already got it solved for dA dt. So all we got to do is work over here, come up with a number. Well, we look at here, the instant when the radius has reached, r was going to, so here is where I can come in and I can plug in 5 for r, right? And up here, I identified that this rate here is my dr dt, so I can plug in 10 for dr dt. So then we get that the derivative of the area with respect to time is equal to 2 pi. Now, when you plug these numbers in, you don't have to plug in the units, but I'm going to do that just so that you'll see that everything works out. Because if we're talking about area, what are the units on area? Squared units, right? And we're going to see that that's what we get. And area changing over time, well, that'd be squared units per time, per second, per whatever. So the r is 5 centimeters. Put that in. And the rate is 10 centimeters per second. And again, sometimes this might get cumbersome, but so what do we get? We get 2 times 5 is 10. 10 times 10 is 100. So that gives us 100 pi. Centimeters times centimeters gives us centimeters squared per second. Doesn't that seem like units that would be on an area changing over time? Yes. So these are so many centimeters per second. 100 pi. We could leave it that way if you wanted to. That is a valid answer. But how many of you really get a good feeling for what 100 pi represents? I don't. But we could take pi as 3.14. So I'll go up here. So you take 100 times 3.14. You could put more decimals if you wanted. And that's going to give us, right, our final answer would be 314 centimeters squared per second. Now it feels a little bit, okay, 314 centimeters squared. What is that? Okay, that's our final answer. Because that's the question, is how fast is the area increasing? That's it right there. And again, like if this was on a test question, that's plenty to show. I probably put in more than I needed to. We don't have to have the units down here. So that's all good. Does that make sense though? Just kind of, once you get it set up, take its derivative, and then from the question you're going to be able to fill in most of the numbers. There'll be one thing that's left unsolved, and that's usually what the question is, and we're good to go. Okay. What I've done is the slides after this are the textbook walking you through, or you could read through this, and this will do exactly what we just did, right? Again, it's more words, but they're identifying that the rate of change was the 10 centimeters per second, and then they say, okay, that's dr dt. Kind of we jumped in. There's a variable r, so that's going to be its rate. They read down further that they wanted to know when the radius was 5, so that's going to say, oh, someplace we're going to plug in r equals 5 for the radius. And since they want to know how the rates of the area is changing, they identified we need to know dA dt. Again, we kind of did all that. Came up with the equation that we're going to use. Again, it's just sitting out there, area of a circle. And then they work through it, just like we did, plugging in the 5 and the 10 at the appropriate time, getting the 100 pi, and then taking the pi is 3.14, multiplying it out, getting to 314. Okay, so it's all there if you kind of want to go through that. And same thing with this one. We'll work through it, and then the textbook kind of will slowly write it out, just if you need to take another look. So this is a different setup. It's not a circle. So we've got Jane is at the top of a 5-foot ladder. The top. And then it's going to start to slide down the wall. We've given here, as we're reading, a rate. So that's a rate is going to be what? A derivative. So just think, translating the English into the math symbols as we go. A rate of 3 feet per minute. Again, that derivative is a constant change. So, which is nice. Then we've got Jack is standing on the ground behind her. Maybe he should have been holding the ladder. I don't know, but that's not the math. How fast is the base of the ladder moving when it hits him? So maybe he's further back, I guess. If Jane is 4 feet from the ground at the instant. A lot of stuff. Where does everything go? Well, this is one where it's going to help if we draw a diagram. So you'll see my extensive art skills. Actually, my mom was an artist. She did some great paintings. I guess I didn't get those artistic genes, but we'll see. So here's my ladder. I'm going to lay, the ladder is, they don't tell us a lot, but we'll assume it doesn't change size. It's a 5-foot ladder. So I'm going to put that as 5 foot. Jane's up here at the top, which, all ladders say don't stand at the top, so she's already being dangerous, standing at the top of the ladder. And here's Jack, who's just not paying attention. Again, he should have been doing his job and holding the ladder. What was happening is the ladder starts moving downwards, and it's got a rate of 3 feet per minute. So I'm going to label that. So what are some things that, and then what we want to know, the question is, how fast is the bottom of the ladder moving? And I'll put with this arrow at a particular time. So before we start plugging in things, though, we need a couple more variables. So what do we have? Well, we don't know exactly how high up the wall the ladder is at any given time. So we'll introduce that as a variable, and that's something that's changing, right? Because the ladder's sliding down. So the height, the top of the ladder on the wall, that's something that's changing. I'll call that H. This bottom part, how it's, looking at this triangle, there's a base here, and again, it's going to change over time. I don't know how much it is at any given time, but it's going to change, so I'll just call it B. Now the thing is I see this ladder that forms sort of a triangle with a wall that I'm assuming has a right angle, right? Does this suggest any type of formula, any type of math equation? Triangles, right triangles, sides of right triangles, Pythagorean. Yeah, so this is our, what we're going to get is the two legs of the triangle are h and b. So h squared plus b squared equals 5 squared. And again, they didn't give us that, so in some ways this is the hardest part, getting to what, but you have to kind of draw the picture. There's no real mention of triangle in here. You had to get that from the picture, and then this is what we're going to need. I think there's a similar one in here, so that's why we kind of give you a little bit of hints of what to look for. So we could, 5 squared, I could write that as 25. Why not? H squared plus b squared equals 25. So we've got our variables in a relationship, a mathematical relationship. We just now need to set this in motion. And how do we set things in motion with math? We do some calculus. We take a derivative, because the derivative will give us a rate. Okay, so it's at this point we'll go ahead and take the derivative. So what's the derivative of h? The 2 comes down. Subtract 1 from the exponent, so we get 2h, and we took the derivative of h with respect to time. And again, that's sort of the strange part. Where's time? Well, it's because things are changing and time is flowing. So that's where that comes from. The base also, we take its derivative. The 2 comes down. Subtract 1 from the exponent. We've got b to the first power. And again, here we took the derivative of the base with respect to time. This is the easy part. What's the derivative of 25? 0. It's a constant, yeah. Square root of it, yeah. So whenever we have a constant, its derivative is 0. And again, be careful here. Yesterday they asked, well, why did you set it equal to 0? I said, I didn't set it equal to 0. Remember, I took a derivative. So sometimes we have problems where we have to set it equal to 0. So you're thinking like with quadratics or something. This one we didn't. We just took the derivative. So had that been like 25x or something, we might have more. But it's just a constant, so its derivative is 0. There's no variable there, so there is no d something with respect to time. Okay? Now that we have the derivative, it's time to go back to the question and see if we start plugging things in that we were given. So we were given that there's this rate here of 3 feet per minute, and well, if you watch the video from Mondays, I just went ahead and called it 3. But is that going to be a positive or a negative 3? Because the height's getting less. I left it as positive, and then I fixed it on the back end and said, oh, because then the other thing was negative. I said, no, this one should be positive. So you could do it either way, but so it'll work if you just put 3, but then you'll have to make an adjustment. But if you say, oh, 3, it's going down and the height's getting smaller, so that really should be a negative rate. So we're going to put that in for, let's see, that's the height. So this is our dh dt. Change colors here. So dh dt we're going to put in as negative 3. And then what do we have? So that's the 3 feet per minute. There's this thing, 4 feet from the ground hits Jane if Jane is 4 feet from the ground. So we know that at this particular instant, this height here is 4. So I could plug that in for h. I don't have the b, so I'll go with 2b. And the question is, how fast is the base moving? That's the derivative. I want to know db dt. still equal to 0. But I have I have two variables here. I still have b there, and I have dB dt. I'm kind of stuck, aren't I? Or am I? Let's go back to the thing. Okay, now I know that the height is 4, and I know this is 5, so I know I have a triangle that is 4 on this side and 5 on this side. Could I figure out what b is? Yes, I can. So I've got to go back now actually to this original here. Now you might have, if you anticipated you might need that b, you might have plugged in the 4 and figured it out already, but I just kind of want to get through this, kind of go through, and that I didn't figure it out till here. You might recognize Pythagorean triples of there's a 3, 4, 5. You're going to see that this is 3. But using this up here, we've got that 4 squared plus b squared equals 5 squared, right, from just using the standard. 4 squared is 16. And if we subtract it over, so let's go 16 plus b squared equals 25. You're going to subtract 16 from both sides, so that will cancel that out, right? You'll get that b squared. 25 minus 16 is 9. B squared equals 9. Square root of both sides, b must be 9, right? Or b must be 3. Square root of 9. Yeah, so don't go too fast. You'll mess up. So square root, b has to equal 3. So we can come back here, and now, because that's the thing we've got to do with math, we've got to get that final equation down to just one unknown, because otherwise we can't solve for everything. We'll plug that in. So we did that, and now we can just do the rest of the arithmetic. 2 times 4 is 8. 8 times 3 is 24. So we got negative 24. 2 times 3 is 6. dB dt equals 0. Let's add 24 to both sides. So we get 6 dB dt equals 24. And then we divide both sides by 6. So I'll do that in green. So dB dt, let's go up here, is 24 divided by 6, which is 4, right? Equals 4. And so that means now it's not 4 feet, but it's 4 feet per minute, right? Because so I guess it's not going too fast, about 4 feet per minute. It's fast enough. But that's our answer, 4 feet per minute. Okay. So see that, again, I would say probably the hardest part is seeing that, well, I got a triangle, Pythagorean theorem, that's it. Take its derivative, and then make sure you have all the pieces. Again, the question itself gives us some things. It gave us the 3 feet per minute. We had to know that was going down. Again, it worked okay. I just did it as positive 3, and I got to the end and I got a negative. I said, wait, it should be the other way around. Okay, I'll call this negative and this positive. We can do those types of things. But that's what you're going to need to do, is figure that once you get that equation that you're going to get set up, take its derivative. Again, we're using the implicit derivative stuff we did before. Questions on that one? Does it seem okay? Okay, let's see. So, and then this will just, if you wanted to review, kind of read through it, this does basically what we did, maybe a little bit more organized. They came up with the height and the base. You could use X and Y. You could use other variables as you want. They identified that the ladder was going down, so they have negative 3. Again, I missed that part initially, but I fixed it later on. And they start identifying some things, then they draw their picture. I drew the picture first because for me I needed to have a picture to see, to, to get it for. One of the things that you struggle with, that I struggle with this is, if you plug in the 4 too soon, then when you go to take the derivative, you're taking the derivative of a constant and you get a 0 and you don't get all the stuff you need. So you kind of got to get sort of just a general equation with all the variables, take its derivative. That's when you start plugging in the numbers. Okay. And again, they come up with a Pythagorean theorem. They take its derivative here, and then their solution. They kind of did the same thing I did. They knew they had these things to plug in. But then when they did that, they were recognizing they still had this other variable that, they got two unknowns and they had to do something. So that's when they went back and say, okay, let's solve for b. And then they got that b was equal to 3. We could plug it in, solve it through, and then we get our 4. Okay, so that's, again, it's all there for you. These next, I think I've got just 2 more, and these will be directly examples from the homework, so I'll kind of read out when I copy and paste them. It's not real large, so we'll see. One of the nice things about these ones is they do give us the volume of a sphere, so they're not expecting you to memorize that or have to look it up. If they have a question on the exam with the volume of a sphere, they will give you the formula as well, so you don't have to try to memorize this particular one. But you do need to know area of a circle is pi r squared. You would need to know the Pythagorean theorem, so we'll practice those. Okay, so we've got a rather flimsy spherical balloon that is designed to pop at the instant its radius has reached 3 centimeters. So that looks like a number that might be important. We'll circle that. And that's not a rate, right? It's a radius. It's an amount. Assuming the balloon is filled with helium at a rate, so if we see the word rate, what do we have? A derivative, right? It's being filled with helium at 15 cubic centimeters per second. And again, we see this word per, so that indicates to us that's a rate, that's a derivative. And calculate how fast the radius is growing. So that's a derivative, that's the question, the instant it pops. So let's think, what do we have? We've got this balloon, we've got a radius changing. The volume must be changing, so that's why they give us this. So the amount of helium being pumped in is going to directly affect the volume, right? So what I can do now is I can identify this particular rate here of 15 as the derivative of the volume, the dV dt. This question, how fast this radius, this is the question we're going to be looking for, is dr dt. That's the question. And we have up here that the radius, this particular time we're looking at thing is when the radius equals 3. Okay, so again, I've kind of identified a few numbers. I've identified a equation. With a nice little hint. And then now let's set this in motion by taking its derivative. That's how we bring in the aspect of time. So the derivative of v is a variable. It's like v to the first power. Take its derivative, it becomes 1 times dv dt. So I took the derivative of volume with respect to time. So that's a marker. The derivative itself is 1. On this side, 4/3 is a number. It's going to tag along. Pi is a number. It's a constant multiplier. So those both stay right where they're at. R is a variable, so I can take its derivative, r to the 3rd. The 3 comes down. So I'll put it in the very front. That's at 3 coming down, and then I subtract 1 from the exponent, so I'm going to get r squared. And then I have to put the marker that I took the derivative of r with respect to t. Okay, so those are, got everything set up. So once we got our equation, take the implicit derivative. Now we're in good shape. Now we go back and try to plug in some numbers and see if we've got just get it down to just one unknown, which we should do a pretty good job here. So I'm going to go ahead and erase this 1. I just use it as a tool that I took that derivative 1 times dr, so I don't have to rewrite this whole thing. The other thing we might do is simplify a little bit, right? Here's 3 divided by 3. Those are going to be just 1. So now we've got this. And then let's go ahead and plug in things that we know. We know dV dt, we were given that it's 15 cubic centimeters. So put in 15, and it's expanding, so that would be positive, right? We've got 4 pi. These 3's canceled. R, let's see, do we know? Oh, we know R. R is going to be 3. It pops when it's 3, so that's the time they want it, when the radius is 3. So we'll have 3 squared. Dr dt we don't know, but it's okay because there's always going to be one thing we don't know, and that's what we're solving for. So we're down to one thing. We just need to do the rest of the algebra, the math. So we've got 15. 3 squared is 9. 9 times 4 is 36. And 30, so we got 36 pi. But we looked up here, they want 2 decimal places, so they probably want us to take pi times 36. So 3.14 will probably be close enough. 3.14 times 36 is 113.04. And then to finish our solving, we just divide both sides because we want to get dr dt by itself, right? Divide both sides by 113.04. And so if you take 15 divided by 113.04, oops, I did something wrong. 15, oh, I timesed, divided by 113.04, yeah. We end up with 0.132, so the 2, we rounding it, it stays 1.3. That's our dr dt. So what that means, at the instant that it popped, the radius was changing by 0.13. What's our units? Centimeters per second. Okay, so that's our answer. And again, we could per second. Okay, questions on that one? Is it kind of sinking in? Okay, and again, it's just sort of this, get this process. Once you get your equation, take its derivative, that's when we plug in all the stuff, all the numbers we know. Hopefully we get down like this one, just to one unknown, and we're good. Now we'll do one more that is more of a business type problem, and I think they've got 2 different versions of this question in the homework. What I want to highlight though is, because as you start preparing for the test, remember, one of the other sections we talked about, they gave us a cost function, they gave us a total cost function, they wanted the average cost function, right? So we had to make the average cost function by dividing by x. In this one, they are giving us already the average cost function. And how do we know that? That little bar on top. If they give us C of x, that is the total cost function. If they want the average, that's what we divide by x. But this one, they've already done it for us. So just be careful, because again, as you go through a test, if they, I don't know that they put two of these right by them, but just watch for that little bar. So that's one of the things in mathematics, little symbols, little changes make a big deal, right? If I make a number small and put it up, that's an exponent. It's different than if it's big and it's on the line, it's multiplication. So those things are going to make a difference. So the average cost function for the weekly manufacture, so again, we've got time in here. It's weekly manufacture of portable CD players is given by this function. And our units are dollars per player. So this gives us how much on average it costs us to make a player. And then it tells us X is the number of CD players. So the nice thing of this is they've already defined our variables for us. But just remember, X is the number of CD players. And then they give us weekly production is currently 4,000 players. So that's a particular time. This is X equals 4,000. And is increasing, so that increasing is changing at a rate. So this is a rate, changing rate, increasing rate. This is a derivative, right? So that's what we have to see, the word rate, and we see players per week. Those are the two things we see. This is a derivative, okay? So that's, and what is it? It's a derivative of the number of players. So this is actually dx dt equals 400. So that's the other part of this, is you've got to make sure you're plugging the right things. You know, one is for the variable, the other's for the rate, for the derivative. And then the question, what is happening to the average cost? Well, I don't know. The question is, so what is it changing? They want the derivative. They could have been more specific. What is the rate of change of this? But so we're looking for the derivative of the average cost function over time, or of the average cost, right? So that's what we're going to look for. So now the nice thing is they gave us the equation. We just start with what they gave us. The average cost function equals 100,000 x to the minus 1. I'm just copying it down. It's 3. Make sure you get enough zeros in there. Okay. So what's our first step? We've got this. We don't plug anything in yet. We need to set this in motion by taking its derivative. Okay. And again, derivative of the average cost, C bar, is going to be the derivative of C. Now remember, again, think of this as a variable, just like y or something. So its derivative is 1. I always like to put that there. And then we put the marker, derivative of average cost over time, dc bar over dt. Okay, so that's it. And that's what we're going to be looking for, which is cool because it's already been solved, right? 1 times this. Okay, now we start to take the derivative over here. We've got x to the minus 1. The negative 1 comes down in front, so this is going to be negative 100,000. Right, negative 1 times that, that's negative. We subtract 1 from the exponent, so this is going to be x to the minus 2. And then we just have to remember we've got these two variables and we're taking the derivatives over time. We need the marker. This is derivative of x with respect to time. Okay, and again, that's kind of more of an abstraction. It's only there because things are changing. Derivative of 20, 0. It's a constant, no variable, so that's gone. Boom. 0.006x, remember this is just x to the first power, so its derivative is going to be 0.0006 x to the 0 power, which is 1. And then again, since we took the derivative of x, we get dx dt. So in this case, we've got two places where we have that dx dt. Okay, that's a lot of work, but we're not done yet. Now what do we do? Let's see if we can plug in some numbers for values, and that's where this stuff up here is going to be helpful. We've got the derivative is 400. We've got that x is 4,000. And that's all we got, but that's all we really need. So I'm going to change colors here. What we get is that the derivative of the average cost is 100,000. X is 4,000 to the negative 2. Dx dt is 400 plus 0.0006 times the derivative of x with respect to time, which is 400. So it's cool. We've got, now it's just all arithmetic, nothing to solve, so just 100,000 times this. Let me get out my, so we can actually just enter this all in. You're going to take 4,000 squared is going to be a fairly large number anyway. So I'll do this in these two pieces here. So negative 100,000 times 4,000 raised to the negative 2 times 400, and I get that this whole value here is negative 2.5, and then I'm going to get plus 0.006 times 400. That's 0.24, positive 0.24. So when we combine these, we end up with negative 2.26. And what is that? Remember, that's the rate of change of the average cost. So it's kind of like well, it is a marginal, right? Over time. So on the weekly, if they produce another one, right? The rate of change of the cost is going down. So if we produce another one, our average cost, not just the cost for that last one, but the average cost overall is going down by $2.26. So that's the rate of change. This is so $2.26 per CD player per week, right? Because that's our units. So that's what's happening is, oh, okay, let's make some more. Our costs are going down. But, we put more on the market, maybe we can't sell it for as much either. So that's why we have, business has all these different things. Is you might be able to be more efficient and save yourself some money on cost, but the people who are selling it says, no, we don't want that many out there because then that's going to drop the price, and so all those things. But again, on these, you're given the equation, take the derivative, plug the stuff in, and go. So that's 12.5. Thursday we'll have a day of review. Again, start looking at the review stuff for all these sections as we go. We'll have the weekend. Get ready for that next test, and let's do well.